Sixth graders at the Healey learn how to design and build bridges through this science PBL under the guidance of Healey science teacher, Mr. Amatrano.
Kelly and Lexia will do this. You do the journal.
The success of project-based learning lies in the planning that goes into it. A well-planned project in science is purposeful in how it directs students' learning of key science practices.
And the key standards that I had were talking about bridges, the types of forces that are on them, and then also some engineering and design process that hit the standards for this project. And what I really like to do when I plan my science projects is look at the next generation science and engineering practices, those 8 practices, to try to make sure that I'm hitting those strategies in my planning and in the implementation of the project. Those practices are things like asking questions and defining the problem, using models, planning and carrying out investigations. So I really like to try to hit all of those practices in one project.
Central to PBL is the driving question, which provides students context and meaning for their learning.
This one I kind of had 2 very similar questions. One is, how could a company or government build the most efficient, economical, and strong bridge for a given purpose? And also, why is it important for governments to take advantage of the resources that are available to them? And how do they use these resources to build the most economical and safe structures for the public to use? So
this project begins with students building content knowledge through labs. For example, in this Forces and Loads lab, students use an online simulator to learn about what kinds of forces impact bridges and how that determines the load a bridge can withstand.
You can actually see how the forces act on a structure. You can see how the box is getting pushed together, and you can also see how this box is getting slid back and forth.
It showed us that when you're pulling it, it's going to become weaker and it's going to break apart. And when you're pushing it together, it's going to become stronger and go together.
So
if they're weight on a structure, sometimes nothing will happen. If there's too much weight, it might fall. Sometimes you have to strengthen it by strengthening the columns.
Formative assessment is an essential component to PBL. As students move through the simulations and labs, Mr. Amatrano uses plickers to check students' content knowledge about bridges.
And in order to really assess them, I kind of do it a little bit throughout the whole project. In the first phase, when the research, I can assess them through their labs that they're creating on Google Classroom, and it's all organized for me right there. And then I also like to do these things called plickers, where students hold up little cards, and it's kind of like a clicker system, and I can ask them a question right at the end of class. They give me their answer. I could scan it with my phone, and all the data is put into the computer. I have it, and I could see what student got that idea or what students didn't. So then I'm able.
Students then begin designing their bridges, taking the content knowledge they learned through the lab simulations. Students have access to limited materials and need to decide how to design a strong bridge using as few resources as possible.
But our general idea is to have 4 supports holding up the bridge, 2 going straight up and 2 going diagonal.
Based off of their research, most of them decide that they should build a beam bridge, maybe with some trusses on the side to help support the weight and distribute the forces, and that they're going to use wood because it's cheaper and pretty strong. That's all that information came from labs that they did on simulators on the computer. So they tie in that knowledge, then they start to design it. They have to create blueprints that they're going to use. Students create.
So we actually decided to make a beam bridge since it's not a long area, and it will be less sweaty than a truss bridge.
Yeah, it's like 30.
Also, that we put 2 strings on each. 4 strings on each. 2 strings on each side. And they're pulling the weight of both bridges, and we're gonna put lots of welding material in the middle to keep it steady, and also pull more weight. And we put X's and triangles to actually carry more weight, because triangles are strong in bridge building. And we put
And we measured how many centimeters it is. So and then we designed it as rectangles deep inside, and then for the roads we use X's in there. So we use like the insides to build this bridge.
Math is an important part of a student's bridge design. Students need to utilize their knowledge of measurement to determine the size and spacing of the components of their bridge.
Where to put the whole thing is 35 centimeters. The middle water part is 15 centimeters. Each of these boxes on either side is 5. The middle is 4 where we cut out, but that's just part of the 15. And in between.
This project also includes project management, which involves keeping accounts and not overspending the budget. Students use a Google Docs spreadsheet to purchase materials and to keep track of their spending. As a group, they need to decide where to spend their money that will lead to building a strong bridge.
The graph paper for a start, so you can draw out the bridge, and each sheet is 100,000, and we got 4 sheets, and so we had to subtract.
I found a spreadsheet template online that the students were able to access, and it kind of just kept a clear idea of what kind of accountants do.
Yeah, we comment and we type it in and he'll see it, or we ask him, what else do we need? And then after we do that, we have to approve it with our project director.
Students also use a Google Doc to keep a journal to track their work on the project.
The journal is like my thoughts of how my coworkers are write about whose job is, and then I'm gonna write about what they're doing, and then I'm gonna see then I'm gonna tell how much money we have.
Technology plays a prominent role in that it helps to deepen the learning through this project.
I want to see what types of technology we can use and how we can use it for benefit, not just for the sake of saying we're using technology, but really help the students learn. I was able to set up a Google Classroom website for the students to access all the different types of labs we did and different types of accounts for the project. Now, students were able to complete labs. So, for example, this is a lab on the different type of forces that the students had to look at. So, students looked at this, and then they were able to complete questions on this lab, keep their notes. And now this is organized. Students then reference back to these notes when they're in their planning phases of their projects.
The bridges are then tested at a family breakfast where students have an opportunity to explain to families and community members how they made their bridges.
Our ideas were not supposed to be like that. We didn't want a suspension at first. We wanted a truss, one that had sides to the bridge, yes, and at the top.
Right. You think it would have been more solid?
Yes.
So
Mr. Amatrano goes back to the driving question by having students analyze the data from testing their bridges to deepen their understanding of how to build the most economical and strong bridge for public use.
One graph is going to show how much did they spend, and one graph is going to show how much weight did it hold. And together as a class, we're going to have that discussion on which team really did a better job, because if one group spent all their money but held the most weight, is that really what we want? Or do we want another group that kind of didn't spend all their money, had a decent amount left in their budget, and still held a decent amount of weight? So we're going to have those discussions and come up with the best as a class.
It's a suspension bridge that we are building, and we're going to use the cable so that way we can connect when we're going to put some weight in here, so that way these can go back and after it can still stay straight, and we're going to